Neutrino literally means tiny neutral one, right? We think they carry no net electrical charge, and they're really, really small, so we call them neutrino.
In 2023, deep beneath the Mediterranean Sea, a ghost particle slammed into a neutrino detector with energy so extreme it defied everything we know about physics. It wasn't just rare, it was impossible. No star, no supernova, no cosmic engine should have been able to create it. And yet, it came. One team of scientists believes they now know how, and their theory doesn't just challenge one part of physics, it rewrites the entire story. Because if they're right, a black hole just exploded. The impossible visitor. It started with a single hit, one invisible particle colliding with a sensor array at the bottom of the sea. The instrument was KM3NET, a neutrino observatory submerged in the Mediterranean, quietly waiting for traces of high-energy particles from the farthest reaches of the cosmos. What it caught wasn't just unexpected, it was unprecedented. The particle was a neutrino, sometimes called a ghost particle. Trillions of them pass through your body every second without ever touching a single atom. Detecting even one is a rare feat. But this one roared into the detector carrying over 220 peta-electron volts of energy. That's 100,000 times more energy than the Large Hadron Collider, the most powerful machine ever built by humans, can produce. To put it plainly, the energy wasn't just high, it was impossible by all known cosmic standards. Supernovas, gamma-ray bursts, black hole jets, none of these celestial monsters could launch a neutrino to such speed. And when scientists tried to trace where it came from, they ran into a wall. There was no known object or event in that direction with enough power to explain it. So, what does it mean when something happens that can't happen? That's exactly what a team of physicists at the University of Massachusetts Amherst set out to uncover. And what they found could change everything we know about black holes, dark matter, and the origins of our universe. The ghosts Hawking warned us about. To understand their theory, you have to go back more than 50 years. Back to a time when a young physicist named Stephen Hawking proposed something so strange, it sounded almost like science fiction. We usually think of black holes as the remains of massive stars. A star burns through its fuel, collapses under its own gravity, and leaves behind a region of space so warped that nothing can escape it. These stellar black holes are enormous. Some weigh as much as millions or even billions of suns. And once they form, they tend to stick around for a very long time. But Hawking suggested a different kind of black hole might exist. One born not from dying stars, but from the chaos of the Big Bang itself. In the first fractions of a second after the universe began, matter was packed together so tightly that small pockets could have collapsed into black holes on the spot. These were called primordial black holes. Unlike their stellar cousins, these black holes could be incredibly tiny, some no bigger than a mountain or even an atomic nucleus. And because of their size, they wouldn't last forever. Hawking proposed that black holes aren't completely black. Through a quantum process now called Hawking radiation, they slowly leak particles into space. Over time, this causes them to lose mass. The smaller the black hole gets, the faster it radiates, until, in the final moments of its life, it releases a sudden, violent burst of energy, an explosion. The problem? No one has ever observed Hawking radiation. For more than half a century, it has remained one of the most famous unproven predictions in physics. But that impossible neutrino from the Mediterranean might be the first real sign that Hawking was right all along. The Mediterranean signal versus Antarctic silence. The neutrino that lit up KM3NET was a once-in-a-lifetime event. But in a world with two major neutrino detectors, the logical next step was simple. Check the other one. That's where the mystery deepened. The IceCube Neutrino Observatory, buried in the Antarctic ice sheet, has been operating for years, quietly recording high-energy particles from space, just like KM3NET. If a cosmic event that powerful had occurred, both detectors should have seen it. But IceCube saw nothing, not just for this event, nothing even close to that energy ever. This mismatch posed a fundamental challenge. If the event had been a typical cosmic explosion, a supernova, a black hole merger, or a gamma-ray burst, then its emissions would have spread out in all directions. Both detectors would have registered the signal, but only KM3NET did. That contradiction is what sparked the University of Massachusetts Amherst team to take a second look at Hawking's old idea. Maybe a primordial black hole did explode, but what if it didn't behave like the models everyone expected? Their thinking led them into even stranger territory, toward a version of black holes that don't just bend space, but interact with something hidden, something darker. And if that sounds like science fiction, what came next made physicists around the world stop and pay attention. Because if only one detector saw the blast, maybe that wasn't a bug in the data. Maybe it was a clue. Dark charge in the shadow universe. To explain the one-sided detection, the UMass Amherst team proposed something far beyond conventional physics. The exploding black hole may have carried a dark charge. Think of it like this. In our everyday world, electric charge governs how particles like protons and electrons interact. But what if there's an invisible counterpart, a shadow version of charge that operates in a hidden sector of the universe? That's the idea behind dark charge. And instead of interacting with electrons, it could involve entirely new particles. The team calls one such particle a dark electron. In this model, primordial black holes don't just evaporate through regular Hawking radiation. A black hole with dark charge would behave differently. It would radiate in unique ways, triggering a much more violent, directed explosion when it dies. Instead of spraying particles equally in all directions, the burst would fire out like a beam, a focused emission aimed like a cosmic cannon. That would explain why only KM, 3NET, not Ice Cube, saw the event. The neutrino wasn't a global pulse. It was a targeted flash, slicing through the Mediterranean like a bullet, and missing Antarctica entirely. It also opens a door to something even more radical. The idea that dark charge and its associated particles are part of a hidden framework of physics that coexists with our own but rarely interacts with it. A dark sector. One that might finally explain phenomena we've been chasing for decades. Because if black holes can carry dark charge, then perhaps the universe has been hiding a whole set of rules we've barely begun to glimpse. The missing 85%. For decades, scientists have struggled to explain one colossal mystery. Most of the matter in the universe is invisible. Galaxies spin too fast. Clusters of stars hold together when they shouldn't. Something massive is pulling on them. We call it dark matter, and it makes up about 85% of all matter in existence. But no one knows what it actually is. What if the answer isn't some exotic new particle, but millions, maybe billions, of ancient black holes? Not just any black holes, dark charge primordial ones, scattered across the cosmos like forgotten fossils from the dawn of time. That's the second revelation in the UMass team's paper. These black holes, carrying dark charge, wouldn't just die in spectacular explosions. While they lived, they'd be virtually invisible. They wouldn't emit light or radiation, but their mass? Still very real. Still able to tug on galaxies, warp space, and shape cosmic structures. In other words, they behave exactly like dark matter should. If this theory holds, then we've had the answer all along. We just didn't know how to see it. These ancient remnants could be the missing mass that's kept physicists guessing for generations. And their rare deaths, brief flashes of dark radiation, might be our only clue that they ever existed. It's not just a new explanation, it's a new lens for looking at the entire universe. One explosion, one neutrino, one impossibility. Could it all be just a fluke? The team at UMass Amherst doesn't think so. In fact, their calculations suggest something far more exciting. If these dark charge black holes exist, then explosions like the one detected in 2023 should happen roughly once every decade, somewhere in the observable universe. That's far more often than anyone had previously assumed. And more importantly, it means we're not chasing phantoms. We're dealing with a phenomenon that's rare, but not unreachable. With two massive neutrino detectors, KM, 3NET in the Mediterranean, and Ice Cube in Antarctica, already operational, we may already have the tools to catch the next one. We just didn't know what to look for before. Now, for the first time, we have a clear energy signature, a directional pattern, and a plausible theory to guide the search. The idea that black holes die in silence is being challenged. These ancient cosmic ghosts might be going out not with a whimper, but with a bang loud enough to shake the foundations of modern physics. We just have to be listening at the right place, at the right time. And if that next burst hits one of our detectors, the mystery might not stay a mystery much longer.